So this is the last type of spectroscopy that we're going to talk about in lab. This is also the last type of spectroscopy that's in your packet. So when you look in your packet, you're going to see, of course, IR, mass spectrometry, and then you're going to see proton NMR, but you're also going to see carbon NMR. So we're going to talk a little bit here in these last remaining screencasts about carbon NMR, and then some other kind of interesting NMRs that you can see, because remember, we're just scratching the surface. There are whole classes that are dedicated to this. So because a proton and carbon-13 nuclei have the same available spin states, the two types of spectroscopy have a lot of characteristics in common, and this is really helpful for us. In carbon-13 spectroscopy, however, the frequency of the RF radiation that's used to irradiate a sample is significantly lower than that of a proton NMR spectra. And so one of the reasons, because of that, what we see is proton signals are not going to appear on a carbon spectra and vice versa. Okay, we're just not going to see that. Now, one of the challenges of carbon-13 spectroscopy is the low natural abundance of the carbon-13 isotope, right? So if we remember, the carbon-13 isotope is only approximately 1.1%, and the rest is carbon-12, which is inactive. So of your sample, only 1.1% is going to be carbon-13. So what this means for us is that most of the carbon atoms in a sample are going to be NMR inactive. And so that means that carbon-13 tends to suffer from poor signal strength. Right? And so we can get many times a lot of really noisy spectra like what we see here in figure 1736A. Now this is a spectra of 1-chloropropane. And so what we see here is this is a heck of a lot of noise, and it's hard to tell if some of these are, like, for example, it's hard to tell if that's a peak or if it's noise. It's hard to tell if this is a peak or noise. In general, you want your peaks to be 5 times higher than the width of your noise. Okay, so that's, which if you take instrumental analysis or analytical chemistry, that's discussed quite a bit in those classes. So if you want to obtain a really good quality spectra, it often requires averaging a large number of spectra, many times thousands, in a sample. And so what this means for us is that where NMR spectroscopy doesn't take very long, it can take 10 minutes, for example, this might take 10 hours. So this would be something, for example, you might run overnight. Just as a proton NMR spectra can tell us the number of chemically distinct protons, a carbon-13 spectra can tell us the number of chemically distinct carbons. I did also want to point out again that, look, that is a real peak. That is the CdCl3 solvent there. So that peak shows up here as the solvent. You can also see TMS still shows up there as well. And then we can pick out 1, 2, 3 peaks, which corresponds to the 1, 2, 3 peaks here. Now, these are going to follow what we would expect for the protons. So, for example, this peak here is closest to the chlorine, so we would expect it to have the highest chemical shift. And so that chemical shift is there. This second one here, we'd expect it to have kind of the chemical shift in the middle. It's right here. And then the third one is the farthest away from the chlorine. And so we would expect it to show up right there. So the carbons are going to follow that. A few other things to be aware of is each chemically distinct type of carbon atom produces one carbon-13 NMR signal. right? And so that's also very helpful for us. Now, one of the beautiful things about carbon spectra is that I want you to notice there is no splitting here. So each carbon is only going to give us one peak, which times students tend to love. So because carbon-13 nuclei have spin, and they can undergo coupling with other nearby nuclei that have a spin, such as protons or other carbon-13 nuclei. However, under the conditions that the spectra are required, we do not observe signal splitting. And in most of the carbon-13 NMR spectra you're going to encounter, every carbon signal will appear as a singlet. Okay? Now, the reason for this is that there's some broadband decoupling. Which is essentially used to turn off the coupling between the carbon-13 and the nuclei. So in your packet, you are not going to see any sort of coupling. Everything with carbon spectra is going to be a singlet. Now, one of the reasons we do this, or use broadband decoupling, is it's helpful because it causes the signal intensity to increase, which helps with interpretation of the spectra. So what this means for us is we get better spectra, but we're only going to see those singlets. Now, the disadvantage, of course, is that we only see the singlets, but there are different NMR spectra that we can use that can help us with that. So let's look at some characteristic carbon-13 chemical shifts. Again, here is TMS, right? It has some carbons here. So you can see those in red. That chemical shift is at 0. Now, you need to program yourself that we're no longer looking at the protons. We are looking at the carbons. Notice that the range is different for carbons than protons, right? For protons, we go to like 0 to 12. Well, here we're going from like 0, and if you look on up, we are going to get into approximately 220, right? So we are going to see these range from 0 to 220 parts per million. So that's one of the ways you can distinguish between your carbon spectra in your packet and your proton spectra, is to look at that axis. Now, despite the different values for the proton and carbon-13 chemical shifts, the order of the functional groups for carbon-13 chemical shifts is roughly in the same order as the proton NMR chemical shifts. So you're going to find, as we mentioned before, the C of the CH3 is going to be lower, right, for that sp3 carbon than for an sp2 carbon than for an sp carbon. So these go in roughly the same order. You're also going to see a quaternary carbon here that's 30 to 35. We can see bromine, chlorine. The carbons that are attached to those are going to be further downfield, right? We can see carbons in a triple bond that's further downfield. We can see here our aryl groups, the carbons there, as well as the carbons for our aldehydes and ketones, which show up even further down. So those are going to, these are going to mimic or space themselves in the same way as the proton NMR spectra. Now, let's look at an example. So in this example, we have 2-methyl-butanal, and it shows 5 signals, right? Each of which is different in height. Now, if the number of carbon atoms contributing to each signal were proportional to the area, then all 5 peaks would have essentially the same height. However, because each signal represents exactly one carbon atom in the molecule, what we can determine from this is, in a typical carbon-13 spectra, the area under a peak is not proportional to the number of carbon atoms. So in a carbon-13 spectra, the area under a peak is not proportional to the number of carbon atoms that contribute to that peak. Right? So the poor correlation between the area under that carbon-13 peak and the number of carbons can be attributed to that broadband decoupling, which tends to magnify each carbon signal. So the fact that we have everything decoupled and we take lots and lots of different spectra and average them together is the reason integration just doesn't work here, unlike in other proton spectroscopy. Now, if we were going through and analyzing this, I want to point out a few different things. So when I said there were 5 peaks, right, this is due to the solvent. That's not one of the peaks, right, which is CdCl3, right? This is due to TMS, right, tetramethylsilane. And so our peaks then fall as 1, 2, 3, 4, and 5. And so when we look at this, we can go ahead and say, hey, look, that's going to be our carbonyl peak there, right? And then our next peak is going to be the carbon next to the carbonyl, which is going to be there, right? And then this is, and that's also an SP, it's an sp3 carbon, but it's an sp3 carbon that is a secondary carbon, right, instead of a tertiary carbon. And so when we look, I'm sorry, that's a tertiary carbon, right, because it only has one hydrogen attached. This is a secondary carbon, and that's a primary carbon. Okay, so it's a tertiary carbon. We see that in the 4 position there. And so what we're going to see here is this is going to be in the 3. And then, so that'll correspond to the 3 there. And that'll be the 2, which will correspond to the 2 there. And then that 1 is the farthest away from everything and correspond to the 1 there. And so that's how we can go through and analyze these. And that's what you're going to do in your packets. Now, when we look at this, how many carbon-13, so let's do an example. How many carbon-13 signals would you expect for this molecule? And so it's just asking, is there if you go to the next slide, which I'm not going to do, it's asking, is there a unique point of reference in the molecule? Are there any planes of symmetry that make some carbon atoms equivalent? And then how many carbon atoms are there in all? So we can say, if I look at this, there's not really a plane of symmetry. But what I also know is that CH3 and that CH3 are at the same point in the molecule. So they are going to be in the same chemical environment. And so when we look at this, we can say, look, I'm going to have 1 carbon here. I'm going to have 2 carbons here. These 3 guys are going to be in the same chemical environment. And then I'm going to end up with 4 here and 5 here. Now, I always want to go back and look, and I can already tell, because I started from the wrong side, that I've made a mistake. And my mistake is that that's also a methyl group. So that is going to be in the same chemical environment as well, right? Because that's a methyl, and that's a methyl. So all those are methyls, right? So they're going to be in the same one. And so let me just erase and renumber, because it looks like there's just going to be 4. Okay. So let's start here. 1, 2, 3, and then that 4, and that 4 all have the same chemical environment. So this is going to give us 4 signals because those methyls are all the same distance away from that first carbon. If you choose to go on to other programs that have chemistry, there are like graduate programs per se, there are a lot of different carbon spectra as well as NMR spectra. So the ones we've studied so far are what I would consider the basic ones, and they provide really valuable structural information about the molecule. But there are other techniques, and so one of the techniques is called a distortionless enhancement by polarization transfer. So it's called distortionless enhancement by polarization transfer, right? And that's DEPT is what it's called. And that produces spectra where the signals given off by the carbon-13 nuclei depend on the number of protons attached to those carbons. And so frequently information from a depth spectra is simply summarized in the normal broadband decoupled carbon-13 spectra that we can see here. And so what that shows you is it'll say, hey, look, this peak here is due to a CH3, right? And so that CH3 is that peak there. And that CH2 is that peak there. And then you can look and say, well, look, these CHs here are due to the CHs on the ring, okay? And so it'll tell you the CH3 is giving a certain peak. So it will couple those for you as a summary. NMR spectrometers can also produce a variety of two-dimensional spectra. Now, all the spectra we've seen until this point are one-dimensional because they have one frequency axis, which is the x-axis. If you use, and then the second axis we have, y corresponds to the amplitude. Now, this is a 2D NMR spectra, and there are two frequency axes, which are an x and y axis, right? So we see here, right, there's your x, and that's the chemical shift, and then here's the chemical shift here. And then we can see the z-axis, and that corresponds to amplitude, okay? And so this is called a homonuclear correlation spectroscopy. We represent that with COSY. Which is COSY spectrum, and there's an example shown here. So in the COSY spectrum, the 1D proton NMR spectra is shown on both the x and y axes, and the peaks that appear on the diagonal line, which is that black dashed line, are the same peaks that appear in each 1D spectra. The peaks that appear off the diagonal are called cross peaks, which indicates which protons are coupled. So these would be cross peaks, and that helps us figure out which ones are coupled to each other. So for example, if I look here, right, and I follow that up and I can find C there, and then I can kind of go across here and see that it's pretty close to B there, that's a really good indication that maybe C and B are coupled together. And then if I come here and I see where C, it lines up here with C, that's a pretty good indication that B, and this is not perfect, right? mean, I'd love it much more if it was lined up over here. So just be aware that these do help with those coupling agreements. Another type of 2D NMR spectrum comes from a heteronuclear correlation spectroscopy, which is called HECTOR. So this is a heteronuclear correlation spectroscopy. Right? And so we can see this is diethyl phthalate. And what we're seeing here again is we've got a carbon-13 spectra shown on the x-axis, and then the proton spectra is shown on the y-axis. So carbon-13 and then the proton here. And each cross peak is going to provide information about the protons that are attached to the carbons. So for example, if we look at these red arrows here, you can see that the carbon at E corresponds to the proton spectra here. So it's saying, hey, look, this is a quartet, and it's going to correspond to this spectra here at E. And of course, we can verify this looking at the structure of the molecule. And you can see they've really nicely labeled it for you here. So two-dimensional NMR spectroscopy from the Cozy and Hector spectroscopy become much more important in the elucidation when molecules are more complex than the one given in examples here, like proteins. Proteins are much more complex. Moreover, there are a lot of other 2D NMR techniques, each which provide distinct information about molecular connectivity. You can also get into 3- and 4-dimensional experiments and still other NMR techniques. So kind of the end idea here is that we're really just scratching the surface. As you continue on, and you may not continue on, but if you're going into the medical field, NMR is used for quite a lot. Mass spectrometry is used for quite a lot, particularly with some cancer studies. But if you tend to go on any more into chemistry, you can specialize in NMR. And there are just so many different techniques, and we're just scratching the surface here.